Alright, we're going to do number 35 from chapter 13. The question reads, a satellite of mass 200 kilograms is placed in Earth orbit at a height of 200 kilometers above the surface. So we have good old Earth with a satellite going around the Earth, and this distance here is, we are going to label it, well, the total distance is from the center of the Earth to that point. We're going to label big R, and this is the radius of the Earth plus 200 kilometers, and then the mass of the satellite is 200 kg. Actually make that a small m, and make the other one make these small because I don't know, you guys might want to do this, but save the constants of Earth as like the the radius of like big R, label this in your calculator, big M, that kind of thing, in your calculator, so on test day it's easier and you don't have to worry about those numbers. So assuming a circular orbit, how long does the satellite take to complete one orbit? So we derived these equations in class, but I can do it now. So using Newton's second law, you have all of sum of all forces equals ma. So then you have, and since it's in a circular orbit, it's mv squared over r, and the forces are going to equal each other, so it's mv squared over r equals gm of Earth, little m, over r. And assuming a circular orbit, how long does it take? So we need to find the period, and we can do that by so first let's find the velocity. So then the r's would cancel, and you would get the m's would cancel too, so you get g m over, okay, this is squared, over r. And then from there you have the velocity and you're trying to find the period. So big T equals, it's going to equal velocity, or T is going to equal velocity over, x over velocity, because T is the inverse of the time. So you get 2 pi r, and actually that's little r, not big R, over the velocity that we just solved for, which is g m e with the subscript over r. And now we just plug in our variables, and you get t in seconds, and then you're going to want to convert that to minutes and then to hours, and in hours you should get 1.47, and that is for A. For B, we also derived this in class, and actually I just derived it here. Velocity equals the square root of the gravity constant, mass of the Earth, and then the radius that you are hovering at, or orbiting at, excuse me. Which we already saved. So again, you just plug this into your calculator, and it gives you the answers in meters a second, and you're going to want to convert that into kilometers a second because the answer is pretty big, and you will get 7.79 kilometers a second. C. Starting from the satellite on the Earth's surface, what is the minimum energy input necessary to place the satellite in orbit? Ignore air resistance, but include the effect of the planet's rotation. So, you can do this multiple ways, but I did it through conservation of energy. So Ki plus U I plus some amount of energy equals Kf Uf. So this is gonna get a little messy. Let's read the homework. So then rearranging, you get E equals Kf minus Ki plus Uf minus Ui. And then from there, you know, the K's are going to be m over 2. Velocity final is the velocity from B, so I'm just going to label that B squared minus the velocity initial, which you also need to solve for. But it's basically just this equation. It's going to be squared, so it's going to be the constant g over the mass of the Earth and then the radius of the Earth. So that's actually big R. And then this gets tricky with negatives, but you know from your equations that the potential energy due to gravity is constant g, big M, times little m, and little m is our 200 kilograms from earlier. And I'm running out of room, but this quantity down here is 1 over the initial. So since it's negative, it's going to flip-flop, but like our positive one's going to be first. So this is our initial term, and this is going to be our final term. But 1 over our initial, which is r, because you're firing it from the surface of the Earth. And yes, that is big R. Minus 1 over RF, which is r little r, and then our little r. And after, plugging that in a calculator, you're going to get E equals 6.43 times 10 to the 9th joules.